This video will explain the theory of computing net atomic charges with the DDEC-6 method. Materials are composed of atoms. Atoms have neutrons, protons, and electrons. The number of protons minus electrons in an atom is called its net atomic charge, NAC. The specific NAC of an atom affects how it interacts with other atoms in the material. Some of the key physical and chemical properties of materials are determined by the collection of all NACs in the system. The study of chemistry would be impossible without the understanding of such properties. The NACs show which atoms in the material are anions and cations, as well as quantify the charge transfer between atoms in materials. NACs can be used to understand the electrostatic and chemical properties of atoms in materials. Historically, NACs only often represent one or the other property. Now, a method is introduced to use a same set of NACs to give accurate electrostatic and chemical properties. A density-derived electrostatic and chemical method was first introduced in a 2010 research article. Over time, there has been various generations of the DDEC method. The ones released for use were the DDEC-1 through DDEC-6. The DDEC-1 and 2 methods were a combination of the iterative Hirschfeld IH and the iterated Stockholder-Adams methods ISA. The DDEC-6 method does not include either of those because it has a different functional form. Among the problems fixed by DDEC-6 method and encountered in IH and DDEC-3 is the runaway charges that resulted in assigning different NACs to equivalent atoms in a material, such as manganese bulk, rhodium bulk, or the hydrogen gas spin triplet. Another motivation to develop the DDEC-6 method was that under high pressures and for different sodium chloride crystals synthesized by W. Zhang and shown here, it was difficult for DDEC-3 method to retain the core electrons in the host atom, resulting in an overestimation of sodium NACs, displayed in y-axis, for the previously shown sodium chloride crystals, displayed in x-axis. DDEC-6 method fixed this problem. The important features and their purpose in the DDEC-6 method are outlined in this table. First, the partition of electron density distribution is proportional to spherically symmetric weight factors in order to reproduce the electrostatic potential outside the material's electron cloud. DDEC-6 has tail constraints for atoms in order to prevent them from being too diffuse or too contracted. Further, the charge partitioning is done in 7 steps instead of iterating to self-consistency, so that the runaway charges problem is avoided and computational efficiency is attained. Lastly, it used fixed reference ion charges consisting of a combination of Stockholder and localized partitioning for the results to convey useful information about charge transfer trends, core electron binding energy shifts, and reproduce electrostatic potential. The resulting NACs usually follow the Pauling electronegativity trends, have good transferability among different conformations equivalently bonded, and are chemically consistent with atomic spin moments. Additionally, the resulting NACs can be used as input for simulations of biomolecules since they have good correlation with methods that calculate force field NACs, such as CHARMM and AMBER. The following are examples where the DDEC-6 method has been used to obtain NACs. In a recent study, researchers have developed interaction models for metal organic frameworks, MOFs. Since there are several thousand of MOFs that can be synthesized, it is desirable to use computational screening to identify which of these MOFs is predicted to work best for a specific application. This allows experimental testing of a small number of materials which have been identified through computations. DDEC-6 was used to get force field precursors such as NACs, atomic dipoles, and others. They developed a method to assess atom types based on first and second neighbors, and concluded the latter is more efficient in capturing the chemical transferability by comparing the sample standard deviations for both cases. The DDEC-6 method was also used to create a machine learning model to predict the partial charges in molecules. The model was able to predict the atomic charges in drug-like molecules with high accuracy, and was chosen instead of the RESP and ESP methods. In another study, CO2 was activated via catalytic reduction with titanium dioxide supported copper clusters. DDEC6 was used to inspect the charge transfer from copper atoms to a titanium dioxide surface. It helped conclude that one electron or less was transferred to CO2, as well as the oxidation state of copper and the conformation of CO2. These were the references used to make this video. For more information about the method, visit these publications. We want to thank the NSF Career Award for funding this project.